Hey everybody, I want to use this video to talk about how we're going to do hypothesis tests with two different samples. So let's go look at that. So I'm going to go back to the notes here. All right, so last video was about how we combine normal distributions. We did all this stuff. And the next video, or in this video, is going to be about actually doing a hypothesis test. So I want to start with sort of a basic idea. As I mentioned last time, or in the last video, we're going to have these as our hypotheses. And the thing that we did at the end of the last video was we figured out what the sampling distribution of all the differences would be, which would look something like this. So, a couple things. One, this requires us knowing sigma 1 and sigma 2, which of course not going to normally be the case. But let's go ahead and do a hypothesis test, assuming that we know sigma 1 and sigma 2, just sort of as a practice, as a warm-up, and then we'll talk about how to get around that, which is going to be a t-test, just like it was with one sample. Do that. So we want to determine if Swedish men are on average taller than American men. So we know from previous studies, American men's heights have a standard deviation of 2.9 inches, and Swedish men's heights have a standard deviation of 3 inches. So we take a sample of 340 American men, getting a mean of this, sample of 251 Swedish men, getting a mean of that. Is this enough evidence at a significance level of 5% to conclude that Swedish men are taller than American men? So we're going to do this two-sample z-test in just a second, but I'm just going to draw out the whole sampling distribution and shade and all that once, so you can see it all the way through, and then we'll just hit a couple buttons on the calculator to see how that goes. So first thing I want to do is find my sampling distribution, which of course is this. So actually, that's not true. The first thing I want to do is label all the numbers and determine what kind of hypothesis test we're doing, right? And so I know it's going to be a two-sample z-test because I've got population standard deviations for both, right? I have both sigmas. So I'm going to go ahead and label all these numbers. These are going to be a little bit big when I label them, but that's okay. So American men's heights have a standard deviation of 2.9 inches. I'm going to go ahead and call that sigma sub A. Sigma sub A. It's 2.9. Sigma sub S. Sigma sub S is going to be 3. 340 American men, that's my sample size, that's N sub A. Taking an average height of 69.4 inches, so that's X bar sub A. So you can see why you might want to label all these things first. This is N sub S, it's 251. This gets, like, there's a lot of numbers in here, right? And so it's nice to have them all labeled before you start doing your problem, right? Because otherwise there's a lot of nonsense to keep track of. So write down what all the nonsense is first. So I want to do this. I want to find the sampling distribution mu1 minus mu2, and then this standard error here, or this standard deviation here. So the thing to notice is this is all going to go away when I go to the whiteboard. So let me just take a second to think about what all these things are. So let me let you take a second to think about what all these things are. Then I'm going to go to the whiteboard and write some hypotheses, because that's the thing we really want to do. So, all right, so my hypotheses look something like this. A null hypothesis, an alternative hypothesis. So we were testing to see if Swedish men were taller than American men, which is to say we're testing to see if mu sub S is greater than mu sub A. Another way to say that is that mu sub S minus mu sub A is greater than 0. Right, so mu sub S, mu for Swedish men, mu sub A, mu for American men. So this is my alternative hypothesis, and my null hypothesis is that they're equal. Mu sub S equals mu sub a, which you can also write as mu sub s minus mu sub a equals 0. So on the, oh, I did that a little sloppily, sorry. So on the notes, I wrote it this second way, right? I wrote these guys as my hypotheses, which is fine. It's probably easier to think of them like this, but the more useful mathematical formulation is this. So you can write them either way. As far as I'm concerned, this and this are both equally correct. You can do either one that you want. However, I am going to use this one here because I want to think of this right here, mu s minus mu a. And the reason I want to think about that is that what I'm doing when I'm making my sampling distribution, I'm actually using that, right? So 1 is s and 2 is a here. So mu s minus mu a, my null hypothesis says this number is 0. So that is the mean of my sampling distribution, right? And then I have to actually calculate this number right here, sigma 1 squared over n1 plus sigma 2 squared over n2 added together square root. So let's calculate that number, and then this number is going to be 0. All right, where's the calculator? There's calculator. It's got all my old stuff on it. All right, so I'm going to take the square root of, so sigma 1 is s and 2 is a. So sigma 1 was 3 squared, of course it's 9, divided by n1, which was, so that's 251, that's the number of Swedish men, plus 2.9 squared divided by 340. 340 or 341? 340. So this is the standard deviation of my sampling distribution, or the standard deviation of the differences between the two sampling distributions. So 0.2462. Okay, so that means that I want to draw my sampling distribution. Go to the whiteboard, draw my sampling distribution, looks like this. Where the mean is at 0, and the standard deviation is 2.462, or 0.2462. So this is n0, 2.462. No, 0.2462. Pardon me. I don't know what it is with me getting the decimal place wrong there, but yeah, sorry about that. Let's get this right. 0.2462. All right, there we go. That's actually what I meant. And then what I want to do is find out what the actual difference that I saw between the samples was. So let's go back to here. So I've got my sampling distribution written. So the thing I want to notice is that I had x bar sub s minus x bar sub a is 70.3 minus 69.4, which you can see is 0.9, but if that's, it's 70.3 minus 69.4. Oh my gosh. All right, look here, calculator. 0.7 minus 69.4. I don't know if you guys have tried to use the VMware calculator, but it's really laggy. I don't know why. So the actual difference that I saw was 0.9. So that means that when I go look at this distribution, when I go look at this distribution, this right here, this x-axis is all the possible differences between an element of one distribution and an element of the other distribution. So the 0.9 that I got was one of those differences. So it goes on here somewhere, right? So 0.9, I'm going to put that over here, right? 0.9, 0.9. And I'm looking for greater than, right? So that's why I wrote it this way. Being consistent about the subtraction will tell you what you should do in your alternative hypothesis, which will tell you which way you want to shade. That's why I'm being so demanding about writing everything down, right? So there's the area that I found. And so this right here is my p-value, just like always. So this guy right here is p-value, p-value. And so we're gonna find that. So this is normal CDF of 0.9 to infinity with a mean of 0 and a standard deviation of 0.246. Now, I should point out that 0.9 sounds like it's really close to 0, but when your standard deviation is only 0.246, this is like, what, 3.5 standard deviations away? So this number is going to be pretty small. Let's go find out what it actually is. So we're going to do normal CDF. The lower is 0.9, the upper is a lot, 0, and standard deviation is 0.2462. Notice that it's very small, 0.000128, right? E-4 is really important here. So I got 0.000128 is my p-value. Back here, it's approximately equal to 0.000128, which is less than 0.05, of course. Right, so this is what 0.01% is less than 5%, obviously. So we're going to reject the null hypothesis. Oops, sorry, that's not the thing I need to do. I need to make a whiteboard. We're going to reject the null hypothesis. We believe this data suggests Swedish men are, on average, taller than American men. There you go. That's how you do a two-sample hypothesis test. Now, let me show you the easy hit a couple buttons on your calculator way to do it. Right. So let's go back to notes for a second. And so again, you want to notice what all this stuff is. I would love to keep it up while I kept the calculator up, but I can't, as far as I know. So you want to note what all this stuff is, and then you just go type it into the calculator, essentially, and it gives you the answer. You do need to know what your alternative hypothesis is, which, believe it or not, is surprisingly hard to get right. Getting this right here to go the correct direction actually takes some thinking, and is, in my opinion, the hardest intellectual part of doing all of this. I know that sounds ridiculous, right? How can you not, like, that's it? All this distributions and calculations, that's all just hitting buttons in the calculator. This thing you have to do on your own without having some machine tell you which way to go based on the problem. So I actually like to do it like this in 2 steps. I know it sounds excessive, but try it anyway. This is relatively easy to come up with based on the problem, right? We're testing to see if Swedish men are taller than American men. That is to say, mu-s bigger than mu-a. If I then just subtract mu-a from both sides, I end up with this, right? And so if you can write this down, you can get to here, and then this will be the correct direction. The other way to do it is just ask yourself, I know I'm going to have mu-s minus mu-a and 0. The question is just, do I want to, is the alligator eating this direction or this direction? And you have to think to yourself, all right, if the alternative hypothesis is true, right? If the thing we're testing for is true, then what does that mean? Like, which one of these numbers is bigger? And then when I subtract in this order, does that mean that this number will be positive or negative? That's how you have to figure this out. So once you've got that, though, you can just go jam it all in the calculator. So I'm going to go to calculator. This is a 2-sample z-test in your calculator. And I will tell you, 2-sample z-test, not common at all. We're not usually going to use these, but of course we're going to do a t-test in just a second. So if I go to stat and tests and 2-sample z-test right here, it asks for all of these things. So I don't have data. What I have is summary statistics. My sigma 1, so 1 is going to be S and 2 is going to be A. So sigma 1 was 3, sigma 2 was 2.9, x bar or x1 bar was 70.3, x2 bar was 69.4, 0.5, 69.4. Oh no, sorry, I apologize. They put these in such a weird order. It drives me crazy, the order they do on the z-test. I don't know why. So they put the sigmas, then x1 and or x bar 1 n1, x bar 2 n2, right? Do all of them together or do all of them in chunks, but don't mix like this. It's just bad user design or bad interface design. N1 was 251. X2 bar was 69.4 and N2 was 340. And our alternative hypothesis was greater than. mu1 was greater than mu2. Mu1 greater than mu a. And then we calculate. And lo and behold, it's the same exact number we got when we did it by hand. Unsurprisingly, turns out that I am telling you how to do it correctly. Yeah, there you go. So this is the sort of thing that I'm going to want you to be able to do on test 3. I'm not going to necessarily ask you to, well, I'm not going to ask you to draw the sampling distribution in shade in this case. There's really not much reason to. I'm going to trust that you guys know how to do a basic hypothesis test and can interpret this screen. So what I really want to see is, can you identify all the relevant data, write a good hypothesis, get your p-value using technology, right, calculator or computer or whatever, and then write a good conclusion that in plain English that describes what you think is true. So that's what I'm going to be looking for. Feel free. In fact, I encourage you to use your calculator, use the tests on your calculator to help you get all the things you need to get p-value and do all the calculations for you. And you concentrate on what it means and what interpretation should be. And this, by the way, this is how real statistics is done. Nobody does any statistics by hand. Everybody uses machines because the calculations are long and messy. And so that's what computers are for, basically. So that's what I want you to be able to do. Understand what the numbers mean, understand where to put them, and then understand what that means as far as the conclusion goes. And that's what I care. So that's what I'll do. That's what I'll be testing. All right, let's go do another problem. Notes. All right. So as I mentioned, these things, the sigmas that you have for your samples, or the sigmas that you have for your populations, you're probably not actually going to have those. So what we have to do is the same thing we had to do before. We had to do a t-test. So what we're going to do here is this. And I know this formula looks a little intimidating, which I'll briefly mention in just a second. We're going to be doing the same exact thing with the t-test that we just did with the z-test, where we're basically just going to be plugging it all into the calculator. Now, here's what you get for your standard error. You still get x1 bar minus, or you still get mu1 minus mu2 is 0, is your null hypothesis. And then the standard error that you get instead of being this will have s's in it. The question is, how many degrees of freedom do you have, right? You don't just have one n and another n, or excuse me, you don't just have a single n to do n minus 1 to get your degrees of freedom. What you end up with for the degrees of freedom is this. This is essentially a weighted, or excuse me, yeah, no, this is your degrees of freedom. This is essentially a weighted average. But as you can see, it's complicated and messy. I'm not going to ask you to do this. Your calculator will just find this for you. So I'm not going to ask you to plug this in by hand. You could, right? It's not super hard. It's just kind of long and messy. But your calculator will just automatically do it, as we will see in just a second. Right? So let's do this question. This question right here. So we want to determine if there is a difference between the average height of American women and the average height of Swedish women. So we have smaller samples this time. We take a sample of 33 American women, getting an average height of 65.4 inches, standard deviation of 2.6. Take a sample of 21 Swedish women, getting an average height of 64.3 inches, and standard deviation of 2.8. And using a significance level of 5%, is this enough evidence to conclude that American women and Swedish women have different average heights? So a couple things to point out. Number one, we do not have any parameters here. These are all statistics, right? You can tell because this and this both are in the same sentence as you take a sample of 33 American women, right? So they're both referencing the sample, and so are these other numbers, the 64.3 and the 2.8, both referencing the other sample of Swedish women. The fact that we only took a sample of 21 Swedish women is not in and of itself problematic. We can still use the central limit theorem because we know that women's heights are normally distributed, so both of these are from normal distributions. It's a little bit of a small sample, as is this 33. So we're not going to be able to be as confident in our conclusion as we were in the men's example, right, where we had 340 and 251 for our sample sizes. Here we've just got 33 and 21, but a tenth of the size. We can still do the test and we'll still get a p-value and everything's going to work out fine, but we're going to be less confident of our conclusion. Third, I'm not asking if American women are taller than Swedish women or if Swedish women are taller than American women. I'm asking if there is a difference, which is to say, if they are the same or not, right? So my null hypothesis is going to be equal to, my alternative is going to be not equal to. So let's go write some hypotheses. Oop, come on. There we go. Let's get a new page. So I'm going to have my null hypothesis and my alternative hypothesis. Null hypothesis is that mu sub s and mu sub a are equal, which is to say that their difference, mu sub s minus mu sub a, is equal to 0. And then the alternative, mu sub s, is different than mu sub a. Now, before I said that I thought it was a little bit easier to use this formulation. And when I was doing it by hand, it was because it directly told me what I was going to use for mu s minus mu a. However, when I'm putting it into the calculator, the thing the calculator will actually ask is this formulation. They'll actually ask for that one. Right? They'll want to know for your alternative hypothesis, they'll write it as mu1 not equal to mu2. So it's actually easier if you're typing it into your calculator to use this guy. So that's the way we want to think of it here, which is nice because that's the easier way to write it. So I'm just going to write down what everything is, right? So I'm going to have x s bar, n sub s, s sub s. We're going to have x sub a bar, got my equal signs, n sub a, and s sub a. Right, so let's go see what those things are because I've actually forgotten. Go here. So American women, I had 33 American women, average height of 65.4, standard deviation of 2.6. Let's write that down. Those are the A's, right? 33, 65.4, and 2.6. We had 33, 65.4, and 2.6. And then for the Swedish women, we had N of 21, average of 64.3, standard deviation of 2.8. N of 21, average 64.3, standard deviation of 2.8. That is the information that we need to type it into our calculator. So that's what I'm going to do. So I'm just going to go straight over to the calculator here. We're going to go to stat, tests, to sample t, this guy, and it's going to want the information that we just had. So we don't have data. Again, we have summary statistics. So here they put them in a sane order. I don't know why it's different for the Z's and T tests, but Swedes, right? X bar, S, and N, X bar, S, and N. So Swedes, we had 60, I forgot. 64.3? Gosh darn it. 64.3, 21, and 2.8. Okay. We had 64.3, 2.8, and 21. And for the Americans, we had I'll go back and look. 65.4, 33, and 2.6. 65.4, 2.6, and 33, and our alternative hypothesis was not equal to. This one, I'm going to talk about pooled in just a second here. Leave it on no. So that's just initial instructions. Just leave it on no. We'll talk about it in a sec about what it means. So calculate. And there we go. We get everything. It spits back all the information that we gave it just in case we wanted to check it. And so we end up with a p-value of 15.6%. So that is not small enough to reject the null hypothesis. Now, I think this is a little bit interesting in that the actual difference between this and this is 1.1 inches, right? Which is bigger than the difference that we got in the men's case. But in the men's case, we could tell that that difference was significant. And in this case, we cannot. And the reason we could do that even with a smaller difference was because the difference was because of the sample sizes. Sample sizes made the, being larger made the standard deviation smaller. So while 0.9 was a big enough difference with sample sizes in the hundreds, 1.1 is not a big enough difference with our sample sizes only in the 20s and 30s. So we get p-value of 15.6%. So here's what I would be looking for on a test. Let me finish this problem off the way I would finish off on a test, or the way I want you to finish off on test. I want to do something like this. T-test with t-test gives, oh, not t-test, sorry, it's a two-sample t-test. So erase that stuff. Sorry, let me get this right. Two-sample t-test gives p about equal to 0.156. So don't reject the null hypothesis. Right? So you write down all this information and say, and I assume that this is what you typed into your calculator, and you get a p-value of that, right? That's what I'm looking for. When you're calculating a p-value, this is what I want. Tell me how you got your p-value. You don't have to write down every button press, right? So this is the information you used. You put it in two-sample t-test, you got this thing. Great. So our conclusion is this is not enough evidence to suggest that American women and Swedish women are have different heights on average. So this is not enough evidence. This is not evidence to conclude that American women, American and Swedish, women have different average heights. Right, something like that. We're not rejecting the null hypothesis, so that means that what you want to do is you want to write this in plain English, right? And if you say something like, this evidence suggests, or this data suggests that American women and Swedish women have the same average height, that's not exactly right, but it's close enough, right? It's better to write something like this. So it's not that we're supporting the null hypothesis, it's that we're not rejecting it, right? So if you want a real life way to think about that, think about if your significant other, let's say something bad happens to you, and your significant other is, whatever. There's, get over it, dude. That's the response that you get. You wouldn't necessarily say that person was rejecting you, but you wouldn't necessarily say they were supporting you either, right? So we're not, this isn't enough to reject the null hypothesis, but that doesn't necessarily mean precisely that we're supporting it, but that is kind of the idea you want to get across to it. We're going back to the default. We don't have enough evidence to say this is definitively wrong, but we're not really saying it's definitely true either. We're just saying we're going to go with the default because we don't have enough evidence here. So anyway, that's my conclusion. So let's go back to the notes here for a second. Is that all I want to say? No. So there's one more thing to say. This formula right here, this messy formula that we just found. Oh, and I want to talk about pooled as well. Is this number, right? The degrees of freedom. Your calculator will find the degrees of freedom for you, and it's not an integer, which is, if you learn what degrees of freedom are, them not being an integer is weird, which gets off into a whole nother discussion, which, believe it or not, involves fractals. So we're not going to worry about that. But that number that I said you will never have to calculate by hand, you won't, because you're just going to do this, right? And the calculator will give it to you here. So 40.37 was the number of degrees of freedom. Notice that this number, this 40.37, is bigger than both 33 and 21. That's because our sample size isn't exactly 33 and it's not exactly 21. It's that we've got the two of them that we're combining, but we don't just add them together either. So I'm not going to worry about where this number comes from or why we do that weird kind of weighted averagey thing. But I do want to talk about pooled versus not pooled, right? So remember when we did this test, 2-sample T gave us this choice of pooled or not pooled, right? And we chose not pooled. Here's what this means. If your sample standard deviations are close enough to each other, you can sort of treat them as both being samples from a larger population standard deviation. And if you do that, then you can do some kind of fancy math. It's not that fancy, it's a little bit fancy, algebra, to get a very slightly more precise sampling distribution, and therefore be a little bit more precise in your conclusion. Right? You can have a little bit more confidence in your conclusion. Now, close enough has a technical definition, and we can't do it yet. I mean, we could theoretically do it, but I wouldn't be able to describe to you what it means yet. You have to do another hypothesis test called the 2-sample F test to determine if the two standard deviations are close enough to each other or not. And the difference that you get out of these by doing that is very marginal. I'm going to run this test again. I'm going to do pooled yes. Remember, we got a standard, or excuse me, a p-value of 0.156, I think last time, 1557, something like that. And so we'll get a p-value that, so our test is going to be a little bit more sensitive now. So our p-value should be a little bit smaller. Let's see what we get. 0.147. Woo, look at that massive difference of 0.008. It's not a big enough deal to worry about. I'll give you on the third test, I'll give you an extra credit question where you have to determine if you should use pooled or not by doing a 2-sample F test. Because we're actually going to eventually learn to do a 2-sample F test, but not until the ANOVA chapter, which, if I remember right, is the second to last one. I never remember if ANOVA or linear regression comes last. But we will eventually learn to do a 2-sample F test, and then we can go back and rediscuss this whole pooled thing. But instead of revisiting that, I'll just make it an extra credit question on test 3 about determining if you should use pooled or not and how to do that, etc. So yeah. For right now, just assume pooled is no, because to assume that pooled is yes means that you're saying this standard deviation and that one are close enough that I can do this fancy math thing or this fancy algebra thing, when we don't know if they are, right? And so no is sort of the safe default choice. It has its own complications, but I'm not even going to worry about that. Just choose no. later on when we get a 2-sample F test, we'll talk about when you would like what you should do to determine if you want to use pooled or not. So with that, I think I want to end this video, and I'll make the next video about doing a difference of two proportions. Right, that's the other thing we want to do, and then the fourth one will be about doing a paired test, so a test where you can pair up your subjects into two groups, or the two groups into basically one group. So yeah, we'll leave that discussion for later. But for right now, I'm going to end this, and yeah, and I will see you in the next one.